Okay, so my last recording got cut off, but what we were trying to say is in this last part of the investigation, we were thinking about when are spheres congruent, which is anytime their radii, these are supposed to be spheres, not circles, but anytime their radii are congruent. If the radii are the same size and the radius goes in any and all directions, then of course the spheres will be congruent themselves. And then when are spheres similar is anytime all spheres are similar because there's only the one dimension that you're measuring on any sphere. There's not length, width, height. There's just the radius. That's it. And so because you always only have that one number, there's nothing else for it to be equal to. It just that is the ratio. This is a 2 to 4 ratio, which of course reduces to 1 to 2, but all spheres are going to always be similar because there's only the one dimension to compare. There's nothing else for it to be equal to. All right, so we're going to kind of change up this next investigation. In fact, by change up, I mean we're going to make it completely different. We were supposed to do an investigation with building blocks, but I didn't know if everybody had building blocks at home. So instead, we're going to talk about some hypothetical spheres. All right, so here are my two spheres. And I just put this off to the side over here on this investigation. I made sphere A and sphere B. And so sphere A has a radius of 3 and sphere B has a radius of 2. And what we're going to do is we're going to look at, number 1, the similarity ratio of A to B. Then we're going to look at the surface area ratio. SA stands for the surface area of sphere B versus the surface area of, sphere A over surface area of sphere B. And then thirdly, we're going to compare the volumes of sphere A and sphere B. So let's start with the similarity ratio. So the only thing we have to compare on these two spheres is their radius. So 3 to 2. That's what we would normally call the side-to-side ratio. A sphere doesn't have sides. Not normally, it never has sides, but it does have that radius dimension that we can compare. All right, for surface area, we know the formula is 4 pi r squared over 4 pi r squared. So for the blue sphere, for sphere A, we're going to do 4 pi times 3 squared. And for the denominator, we're going to do sphere B, 4 pi, the radius is 2 squared. Now, something fun to look at here is we could save ourselves a lot of work in this ratio calculation because these 4 pi's cancel out. And so really we just have 3 squared over 2 squared. And I know we could go ahead and go a further step with that, but I'm going to leave it as 3 squared over 2 squared, and this is 3 to 2. All right, now we're going to look at the volume of these two spheres. So this is 4/3 pi r cubed for volume of sphere A and 4/3 pi r cubed for the volume of sphere B. And so if we fill this in, 4/3 pi times 3 cubed over 4/3 pi 2 cubed. Again, there's a shortcut. Again, we can cancel out the 4/3 pi because that's a common term, a common factor in the numerator and denominator. And so we really just have 3 cubed, over 2 cubed. I'm seeing a pattern here, friends. It looks like that if our side-to-side ratio is two things, A to B, 3 to 2 in this case, then the surface area ratio is those numbers squared, and the volume ratio is those numbers cubed. So we really kind of already knew this one because we knew that side squared compared to side squared equals area to area. Surface area is just a specific type of area. So our new one for today is that side cubed over side cubed equals volume over volume. So these are our new theorems for today. This works with any shape, not just with spheres. It just is the most clear that everything cancels out in the sphere formulas. All right, so let's go. Let's go on down to our theorem. If two solids are similar with a scale factor of A to B, then their surface area, anything with area, is going to be A squared to B squared, and the volumes are going to have a ratio of A cubed to B cubed.